Excitement. That's all we're feeling right now, huh? You're like, fundamental theorem of calculus? Gosh darn. What could be more exciting? We're finally gonna figure out the fundamentals of calculus. I know we're almost to the end. I know it's a grind. We're pushing towards the end of Calc 1. Hey, let's get these two. They're fundamental. Do I need to say more? We gotta know them. And I'll start by telling you, the fundamental theorem of calculus part 1, for the most part, we use it so we can get the fundamental theorem of calculus part 2. So let me just start you off with, you not understanding fundamental theorem of calculus part 1 at the beginning is exactly where you're supposed to be. You shouldn't understand FTC part 1 until you've seen FTC part 2, and then you go back to it. And it really kind of, the light bulbs can go off then. And maybe not, I don't know. But at least for me, once I understood 2, then 1 became a, oh, no shit. All right. But the mechanics of FTC part 1, pretty basic shit. All right, but let's get into it. It's a lot of graphical stuff. How we can do it, well, I mean, I could just make it terrible, but, well, you love graphs, huh? It's your favorite? So let's look at a graph. All right, so we got some function, right? We got some function right there. It's graphed in green. And we're going from, what, some point A up to point, and I haven't written it in yet. Well, we're going to talk about what we're going to go up to. Because I want to talk about a couple other things beforehand. So if you see what's different in this, you have a t in there. So that means your axis down here, I haven't read. Your axis is t, not x, right? So are we okay with that? The t is we're at the t-axis and the x-axis? Because I'm going to have to use x later for something else. Okay. And here it is. Here's the something else. Oops. Try it again. Try it again. X. We're going to say we're going to go from A up to some variable. What this allows it to do, so this X could be like over here instead, or maybe over here. It's just saying it's not a fixed point. All right, A is a fixed point. A is not going anywhere. Once we say A, that's like a constant, like 3. It doesn't vary. But X could be anywhere down the line. So we're giving ourselves some variability down that line that we typically think of X anyway, but we're actually using this little dummy variable we call T. And this is just so we can make our point. All right, now we can say, now this is kind of the big part of everything. So we're going to create a whole new function here. And we can say the area with respect to X. See this X right there? That area with that X right in there. So it's just saying how far from A going down to whatever value that might be, the area is going to be equal to. And that's going to be the integral from A of our f of t dt, right? That's just, oh shit, that's just this, right? We just put our f of t and dt underneath that line. We're good, we're good. Purposely, again, did not put in the what we're going to, but what are we going to? Going up from A to X, that X. So this is saying that the area is dependent upon however far we go. The area with respect to X, we're going to input that X value, not a T value. It's a lot, but we're going to continue to use this little area the whole way down. So let's mess around. So I have a graph a little bit different. We kind of have the same sort of game going on, where this graph, you still got some curve where it says it's from y is equal to f of t, you know, right there. But it's going from one point to another. Now, what's the point? Now, the point's changed. The point changed. I mean, we're still at A. A is not going to change. Now, x is hanging out right here, but we're not going to look at x. We're going to go a little further. We're just going to go a little further to x, plus some other piece, something else. So we say that the area is equal, or our area is area of x plus h. That's saying we're going to take this whole region. We're going to find that area. you were to write it, I'm not going to write it in the integral. I won't write it in the integral. We'll just keep going. So there's the game. Since we went from a up to x plus h, we call it the area of x plus h. And again, t is that dummy variable. So let's see this next one. Now we took the same function, same curve, same everything. X's are in the same spot, but on our next one, we just want to go from a up to x, not a up to x plus h. So we didn't go all the way up to it, right? We don't have quite as much area. It's not quite as much area, but since we're talking about going up to x, that's why that input right there is x. So we have area of x plus h, and we have the area of x. Chill? Chill. Okay, so hopefully you're okay with that. I know it's a lot. I know it's a lot, but your quiz problem's coming in just a second. Actually, I'm going to be a total dick about this. I'm going to give you problem number 1 of Hidden Quiz 5. Oh yeah, you're going to have to come back. Spending too many hours. I want you to hang out with me. I miss you guys. I'm kidding. I just want you to do more work. I want you to be prepared for count 2. I want you to be the freaking... Alright, let me shut up. Alright, and now we go down to this next piece. That's just the part, the difference, right? Isn't this just the difference between these two? It is. Now, let's approximate what that might be. So instead of actually trying to find some sort of integral that goes all the way up to here and finding this shit too, let's just approximate it. Let's just take a look at it. And we'll just create this rectangle right here. We'll call that's the difference between those two areas. About. I mean, it's not perfect, but it's close, isn't it? It's close. I mean, we're missing a little region, so it's a eh. And we can say that the area of this rectangle is, well, that's just... Well, f of x is the height because we're going off of that point there. Remember, x is the input that we're putting in. So f of x, we'll say that f of x is the height times the difference between x and x plus h. That's just h. So we're like, well, the area there is that. It's approximately that. So why don't we use a little graphical subtraction? Look at all 3 of these suckers. So our conclusion becomes that the area of x plus h minus the area of x, right? So the big area minus the smaller area just leaves you with this shit down here, right? But we can't use an equal sign. I'm just going to go, it's about. And we said that area we found in down that spot was about f of x times h. Whew! Through the graph stuff. We're about to get there. And I'm going to get to the end and you're going to be like, what the hell did you just say? It's all right. It's all right. Oh, and here's your quiz problem. Here's quiz 1. Here's number 1. Whoa, I better zoom in on that one. Let's try it again. So, number 1. I want you to write it as a limit of sums. Limit of sums for the integral from 1 to 7 of 3x to the 4th minus 5 ln of x dx. There's problem 1 for your Hidden Quiz 5. All right, going back to our problem. Let's start messing around. Let's start doing a little bit of fancy algebra to this. Do you mind if I want to move this? I don't want this h over here. I think I want to divide it out to both sides. Okay, so let's divide it out, and we're going to end up with x plus h minus the area of x is approximately equal to, and we divided that out. That shit just goes away, and we get f of x. And here we get it over h. So we have the area of x plus h minus the area of x all over h. That should look familiar to you. F it. Let's just keep going. You know what I'm thinking? I see this little h hanging out right here, and it's like, limits, bro. Limits. I love me some limits. Why don't we take both sides of this then? Let's limit it on up, huh? Let's do some limits, and we're going to take the limit. Let's make h go to 0. So we can take those two areas and get them really freaking close together. Think about it. If that h is going towards 0, these two areas would be really freaking similar, wouldn't they? They'd be the same freaking thing if they go to 0. Yeah, there's no freaking difference between x and x plus h. Come on, let's go. All right, so if we take the limit of this thing, area x plus h minus the area of x, so they'd end up being like the same thing. So that would be 0 over 0. Oh shit! And we say that that's approximately equal to the limit as h tends towards 0 of f of x. I don't know what the hell f of x has anything to do with x. I mean with h. You know, I really don't think that there's much that has to do with each other. So I think we can probably just call this f of x. And after we take this limit, you know what? We can actually say that this is equal. We can say that this is equal if we take the limit as h tends towards 0. And what is this? If you don't recognize this, come on. Usually we had f of x plus h minus f of x all over h. That was 2.7 and 2.8 from your old text, huh? So we're going to say that a prime of x is equal to f of x. Therefore, we can say that the derivative on the area function is equal to the derivative from a to x of our f of t dt, which is just equal to our f of x. That's the fundamental theorem of calculus, part 1. I told you. I said, hey. You're going to be like, huh? I'm not even going to try and friggin' explain it. Not yet. Not yet. I'm going to get you in another slide. We'll do some more stuff. Now, let me write it out. We'll get kind of proper and I'll kind of speak some words. So I'm just going to call it FTC part 1. You know what it means. If f is continuous, on some closed interval from a to b, then g defined by g of x is equal to the integral from a to x of f of t dt. We're going to keep that x value in between a and b, right? Like we had it. And we'll say is continuous on the closed interval. So it's defined by that, and it's continuous and differentiable on the open interval. Let me find out, and g prime of x is equal to f of x. That's what your textbook tells you. But we're going to think about it this way. F of x is equal to the derivative with respect to x on the integral from a to x of f of t dt. When I think of FTC part 1, this is what I think. Now, this doesn't have all the bells and whistles in it. This doesn't have all the cover your ass that something from a textbook is going to say. I'm not even explaining what all this means. You know, it's got to be continuous and differential in order for you to be able to take a derivative on stuff. And that's why we're covering our ass and all those words. Right? For something to take a derivative, it has to be continuous and differentiable. So that's why we have to say all this to really make it even worse than it is. And it's already rough looking at this. F of x is equal to the derivative of an integral. But what happens if you take an antiderivative, or what happens when you take a derivative of an antiderivative? You go back to where you started. I'll see you in the next.